Hey everybody, and welcome to my tutorial on setting up a fresh DirectX11 project and integrating Ultralight. The solution for this project will be available for download via a GitHub repository. The download link will be in the video's description. I'm also going to have timestamps for each section in the video in case you want to skip ahead to a certain part. First, let's discuss the target audience. This is intended for programmers experienced in C++, the DirectX11 API, as well as the Windows API. If you want to learn the basics of DirectX 11, I also have another tutorial series covering most of what you'll need to know to understand this video. So what is Ultralight? Ultralight is described as a lightweight, pure GPU HTML UI engine for desktop and games. This is useful for us because we can use Ultralight to easily render any UI in our games and have it all be designed in HTML, CSS, and JavaScript. Ultralight still feels pretty bare bones, but with some creativity, I think you should be able to replace most missing functionality that you might desire. On the Ultralight webpage, you can find information on the licensing if you decide to use this on a commercial application. It may be worth noting that the creator, Adam Simmons, recently mentioned that he might be revising the license model. Before we get into the code, let's take a look at a UML diagram I designed for this project. There is a link to the UML diagram in the video description. In this UML diagram, it will describe the class hierarchy in each of the sections for this solution. The diagram layout will be as follows. The class name will be in dark gray. The enums, if there are any, will be in red. The public functions will be in blue. The private functions in green. And the member variables will be brown. At the top of the UML diagram are utility classes that may be used throughout the solution. Most of them are singletons. We will have a directory helper class to get the current directory, an error handler class, which we will redirect errors to with macros, a MIME type helper class, which will be used to resolve a MIME type from a file extension, a string helper class to convert strings to wide strings, and then lastly, we will have a timer class, which is the only utility class that is not a singleton, and it works just as you'd expect a basic timer class to function. To start off, we're going to be creating our engine class, and our engine class will contain a window object, a renderer object, pointers to our mouse and keyboard objects, and an HtmlViewManager object. For our solution, the first thing we'll need to design for our engine class is our window and input handling. So let's address the windows and input section. We will need a window class to initialize our window, and it will also hold the mouse and keyboard objects, as well as a way to retrieve them for the engine to be able to access them via pointers. For our window class, we will be required to create our mouse and keyboard classes. Our mouse and keyboard classes are going to have queues of either mouse events or keyboard events, and they're going to have ways to read the event buffer to see if it is empty, and if it is not empty, to get the next event in the queue. If you look down at our mouse event and keyboard event classes, note that they both have a way to convert them to Ultralight mouse events or Ultralight keyboard events. These Ultralight events will be passed to our HTML views later to be processed for any HTML views that are in focus. Once our windows and input section is done, we need to work on the renderer and the DirectX 11 side of things. We will create a renderer with beginFrame, render, and endFrame functions, as well as a way to retrieve a pointer to the D3D class instance. The renderer will also hold constant buffers for the orthographic matrix and a world matrix to be used when rendering the 2D views. Lastly, the renderer will hold a PixelShader and a VertexShader for our 2D rendering of the views. For our renderer section, we'll need a D3D class to handle all of the default necessary states for this solution as well as their initialization. We will make a PixelShader and VertexShader class similar to the ones in the previous DirectX 11 tutorial series, as well as ConstantBuffer and VertexBuffer templates to reduce the bloat in related code. Once our renderer section is complete, we should have the ability to render a textured quad. The next part will be the Ultralight integration and creation of the HtmlViewManager class. The HtmlViewManager class will be used to create the views, fire events, get and update the views. It will also contain the file system, GPU driver, logger, and font loader instances to be used by Ultralight. Ultralight has many adapters that we'll need to inherit from and provide our own functionality. First is the file system. This will control how Ultralight reads, writes, and interacts with files. Next is the GPU driver implementation. This is the most tedious part of implementing Ultralight. The GPU driver will control all of the GPU interaction. Next is the logger. The logger will be used to log errors and warnings from Ultralight and how to handle the error message. The last adapter we'll need for the Ultralight renderer instance is the font loader. Our last class we'll need for our Ultralight implementation is our HtmlView class. This class will have adapters to apply to each HTML view. One is for the load listener to tell when the view is loaded, and a view listener to determine when certain things are triggered in Ultralight, such as a console message, or if the cursor changes. Our HtmlView class will also hold a reference to the shared VertexBuffer for the quad vertex data that each view will use and have a way to retrieve a pointer to the buffer for our renderer. Now that we have reviewed the UML diagram, let's create our solution. We're going to use the Windows Desktop Wizard for this. And we are going to select a desktop application and make this an empty project. Ultralight only supports 64-bit applications. So let's go to the Configuration Manager and go ahead and remove x86. I'm going to go ahead and set up this solution to have a dedicated directory for the intermediate build files so that we don't see them when we build the solution. When we go to our project properties, we're able to assign that here in the intermediate directory. And make sure we have all configurations selected so it does it for debug as well as release. And I'm just setting it up so, for example, if I am in debug x64, it will make a intermediate build files folder with x64 and debug inside of it, and then the files will be there. Let's set up a folder for any third-party libraries that we might use, such as Ultralight. We need to download the Ultralight libraries and header files. On the Ultralight GitHub repository, they currently have a preview for version 1.2, so we are going to be using that in this project. If we scroll down, we can see where we have the 64-bit Windows download. Once we extract that folder, we should have something that looks like this. We are going to copy the lib, bin, and include folders, and we are going to place these inside of our Ultralight folder. I'm also going to be renaming the include folder to inc and the bin folder to dll. Next, we need to set up the include directories and library directories. So go to the project's properties, go down to directories, make sure we have all configurations selected, and go to edit the include directories. And then for this, we're just going to use the solution directory macro to get to our include directory. We're going to do the same thing for the library directories, except to get to the lib folder. The last thing here is we want to go to our linker and go to the input section, and we have to specify all of the libraries that we'll need to access here. And for this, we're going to be accessing the Ultralight lib, Ultralight core, web core, D3D11, which is from DirectX 11, D3D compiler, which is also for DirectX, and then dwrite, which is for DirectWrite. So press OK, and press OK. Let's go ahead and create our first source file. And let's create a precompiled header file. I'm just going to call this PCH. And for now, we're just going to include Windows. And then inside of our source file, we'll include the header. Next, we will create our entry point. And a pattern I'm going to follow throughout this video is in the function definitions, all arguments to the functions will end with an underscore. So in case you're wondering why that is, that's just what I'm using for this. Before I create the engine class, I'm going to go ahead and create all of the classes for the utility section that were covered in the UML diagram. I'm going to check show all files so we can see the folder hierarchy for when we create these source files. Create a new folder for our engine and create a folder inside of this for our utility section. In our UML diagram, the first utility class we had was a directory helper class, so I'm going to go ahead and create the header file for this. The directory helper class is a singleton, so all of the functions and members will be static for it. It's going to have functions for getting the executable directory as a string, as well as a wide string. And then it's also going to have functions for normalizing the path. By normalizing the path, we're just going to be converting all backslashes into forward slashes. Let's create the CPP file for this class. The string and wide string versions of getExecutable directory are pretty much the same. We're going to be calling getModuleFileName to get the executables file path, and then we are going to be just cutting off the actual file name from the path, just so we get the directory, and then we are going to be normalizing the path, which is where we're replacing the backslashes with forward slashes and returning that. The only difference between getExecutable directory A and getExecutable directory is we're going to be calling getModuleFileName instead of the ASCII variant, and we are going to be using a wide string here. The normalized path functions work as you expect. They're just replacing all backslashes with forward slashes. We also are declaring our string and wide string for the executable directory at the bottom of this CPP file. Next, let's create our error handler class. I'm going to create a new CPP file. We did something similar to this in the DX11 tutorials. What we are going to do is we are going to have a error handler class, and we're going to have macros that are calling the functions from the error handler class. And the purpose of the macros is they will automatically look at the file that the error occurred in, the function, and the line, and it will be passing them to the function calls in the error handler class to get us more information. We need to include the string header into our precompiled header file. So let's go into the precompiled header and add string. Now let's create the CPP file for our error handler class. Our CPP file is just going to have the functions where we are creating the strings to display in the message box for the errors. The critical errors will just display a message box, but the fatal error functions will also exit the application with an error code of -1. The error handler class needs the string helper utility class. So let's go ahead and implement that. The string helper class just has a string to wide conversion function. Go ahead and generate the CPP file. And to convert a string to a wide string, we can just call the constructor on wide string like this and return the value. We need to add the string helper to our precompiled header list. Next, let's create the MIME-type helper class. The MIME-type helper class will just have a char and a wide char version of converting a file extension to the MIME type. Let's create the CPP. The way that we are determining the MIME type string is just a bunch of if statements comparing the extension that's passed in. It is not elegant, but it works fine for what we need. There was a Windows variant of doing this with doing some Windows calls, but I didn't really understand it. So I just decided to go with the cross-platform solution in the Ultralight app core repo. And of course, we just have the char and ychar versions of this. The last utility class we'll need to make is the timer class. And I believe we had this same timer class in either the networking or the DirectX tutorials. And the timer class just works like you'd expect. You're able to start it, stop it, and get the milliseconds elapsed and restart it. Now that we have our utility classes set up, we can create the engine class. According to our UML diagram, the engine class layout will look as follows. We will have an initialize function, which will attempt to initialize the window, renderer, HtmlViewManager, and assign the mouse and keyboard pointers. A getter function to determine if the engine is still running or if it should be closed. A tick function for processing each frame with the delta time passed as a parameter in milliseconds. A render function to be called once per frame. For the Windows and Input section, we are only going to focus on creating the necessary parts for the window and input. We will not yet be declaring the render function, renderer instance, or the HtmlViewManager instance, so we will comment them temporarily. Let's go ahead and begin defining our engine's functions. Let's also make sure that our engine has access to the precompiled header file. Let's determine what we'll need to do for our engine's functions. The first thing I'm going to change is all of our variables in the actual function definitions will be ending with an underscore. In our initialize function, we will need to initialize the window, and then assign the mouse and keyboard pointers that we get from the window. For our isRunning function, it's just a getter. And then for our tick function, we will process the mouse and keyboard messages. Let's begin our window class. We're going to create a folder called window. That is going to hold all of the window related classes. Let's go ahead and create our window header and include our precompiled header file. According to our UML diagram, our window class should look something like this. For our initialize function, we will set the X and Y position to the center of the screen if they are left unassigned at the max integer value. Our process messages function will process any outstanding window messages and then dispatch them. It will also check if the window was closed and return false if so. We will have getter functions so that the engine can access the mouse and keyboard as well as the other members. We need a function to register our window class because we cannot create the window without registering a window class. We need to hold an instance of our mouse and keyboard classes here, and we will also need to hold a handle to the window, the title, the name used for our window class, and the width and height of our window. Since we will only have one window, I'm just hard-coding the window class name. We can define all of these functions without actually defining the implementation for the mouse and keyboard classes, except for the window proc callback function. Let's create blank classes for the mouse and keyboard classes so that we can go ahead and finish the rest of the window implementation. We will create an input directory to hold our input classes and create headers to declare the mouse and keyboard classes. Now that the mouse and keyboard classes are declared, we just need to include their headers. Let's begin defining our window class functions. All of the function definitions parameters need to end in an underscore to follow the same pattern as before, so I'll go ahead and fix that now. We can easily define the getter functions as they are straightforward. For our initialize function, we will need to do the following. Assign variables based off of incoming params, determine the window's X and Y position, determine the window rect, register the window class, create the window, and then show and focus on the window. For assigning the variables, we will just set the width, height, and title, and then also create variables to hold the X position and Y position. If the window's X and Y positions are not assigned, we will need to determine the center X and Y positions accordingly based off of the screen dimensions and the window dimensions. We can do this by taking the half width of the screen and the half width of the window, and then adjusting the center of the screen by the half of the window's width, and that will get the X position, and then we do the same thing with the Y position to get where the top of the window would be. We need to determine the window rect, which we can just build this with our new X position and Y position values, as well as the width and height. And then, using our window style, we will have to call adjustWindowRect to adjust it to be the correct size based off of whatever styles we're passing in when we create the window. Of course, we'll have error validation so that if for some reason adjustWindowRect fails, then we will return false. I don't know why this would ever fail, though. I've never had it fail before. Next, we are going to be calling the registerWindow class function. For this, we will also need to define it. This is going to be similar to the one we set up in the DirectX tutorials, except we are using the ASCII variant of the window class instead of using the version that takes in wide strings. We are going to use a setup similar to the DirectX tutorials, where we have the default window proc be used to assign the window proc on the window creation message, so that we can call the Windows window proc function callback for the individual window instance. We can see that the pointer to the window proc function is set to handle message setup, but handle message setup still needs to be implemented. In handle message setup, what we are going to be doing is on the window create message, we are going to be extracting the window pointer from the Windows create params. Once we retrieve the window pointer, we are going to be setting the user data for this window to be the pointer to our window class so that we can access the instance of our window. We are going to reassign the window proc to be a different callback called handle message redirect, which we are about to implement. And that way, whenever a Windows message is processed, it will go through the handle message redirect function instead of the handle message setup function once the user data is assigned. Now let's implement the handle message redirect. And for the handle message redirect, for all of our messages except for close, we are just going to retrieve the pointer to our window by accessing that user data where we had stored the pointer before. Once we have the pointer to our window, we are just going to call our window proc callback from our window class. Now that our window class is registered, we just need to create the window. This should all look familiar if you've created a window before. Note that we are passing in this for the last parameter in our call to create window. This is necessary so that our handle message setup function that we created can get a pointer to this window instance when the Windows create message is processed, and then it can use that for setting up the callback to the window proc function. After we validate that the handle is not null, we need to show and focus the window. We will do that just by calling show window, set foreground window, and set focus. And once we get down here, the window is successfully created, so we can return true. Next, let's look at our process messages function. For our process messages function, we will just have a loop to peek and translate and dispatch all existing messages. If we get back a null message, we can check if our handle is still a valid window. If the handle is not valid, that means that the window was closed. We will return false if the window is closed, or otherwise we will return true. Before we can define the window proc callback function, we need to finish the implementation of the mouse and keyboard classes. We are going to work on the keyboard input first. So according to our UML diagram, our keyboard class should look something like this. We are going to have the window as a friend class, and that will allow the window to access the onWindows keyboard message private function. The window proc should be the only function that is ever actually adding messages to the keyboard's event buffer, so that is why we have it set up like this. We are going to have an array for the key states, and that will allow for the key is pressed function to work, where we can just check if a key is pressed at any time. Event buffer is empty, and read event are just for working with the queue. We'll need to go ahead and define the keyboard event implementation. So let's add that header now. The first thing we'll do here is include our precompiled header. And we actually need to add a couple of things to the precompiled header. So I think I added the timer off the video, and I forgot to add that on the video. So we need to put the timer in. We need to include queue, and that way we can use queues. And then we also want to include the key event and mouse event ultralight headers. The last thing I'm going to do is I'm going to have a namespace alias for ultralight, and that will just let us use UL instead of typing out ultralight every time. Now let's go back to our keyboard event header, and our keyboard event class will look something like this. We're going to have an enumerator for the type, and this is just for the type of event that's occurring. And something you'll notice is we have one-to-one matchups for our event that we are creating, or the enumerator rather, and then the ultralight event that we're matching it up to. And this will be good because it makes it easier to convert this to an ultralight event when we need to pass it to the view. We're going to have a default constructor that just creates an invalid event, and then we are going to have the constructor that takes in the message, the W param, and the L param from our window proc callback in our window class. We'll use these values to construct the information for this keyboard event. We're going to have a getter for getting the type, and then functions for checking if the key is a key down event, a key up, if it's an auto repeat. So if you're holding down the key, it can cause more than one event to be triggered. When using the default constructor, the event will not be valid until the type is assigned. So that's why we have the isValid function. And then we're just going to have get key code, and then we are going to have a function for converting this to an ultralight keyboard event. We are also going to be storing the W param and L param, and that will just make it easier to convert this to an ultralight keyboard event because there's a constructor we can call for that. And then we are just going to store the type, the key that was pressed, and then whether or not it is an auto repeat. One more thing I'm going to add to this that I actually didn't have in the UML diagram is we're going to have a function to check if this is a system key or not. What will determine if this is a system key is just the Windows message that triggers it. We will have a system key down and system key up Windows message event, and those will only be for system key events. Let's generate the definitions for all of these functions. First, I'm going to put underscores after any parameters. The default constructor, as we said, will create an invalid keyboard event. So we will just default the type to invalid, set the key to 0, unsigned, and then we'll default the isAutoRepeat value to false. Before we do the main constructor we'll be using, let's go ahead and do the other functions just because they're much simpler. So for the type, we return the type, is key down. We will return whether the type is equal to key down. Is key up will be the same idea. For checking if it's valid, we'll just make sure that the type is not equal to invalid. For converting this to an ultralight keyboard event, we are just going to call the key event constructor. And the one that we'll be using is the last one that we see here, where the first argument is the type. And we can just static cast our type to the key event type because our type and their type is a one-to-one match. Next is the W param, then the L param. And then last we have that isSystemKey value that we're going to pass in. Now all that we have left for our keyboard event class is our constructor that takes in the message, the W param, and the L param. This constructor will look like this. We are first going to store the W param and L param. Then we are going to extract the key code from the W param. We're going to have a switch case based off of the message type. If it is key down or key up, the type will be key down or key up. And then we are going to determine if it is auto repeat on key down by doing this bit mask. The system key down and system key up messages will be exactly the same as key down and key up. The only difference is we are going to be setting isSystemKey to true. The last keyboard message we are going to process is the window message for our characters. And then the default, which we should never have this happen, we are just going to set it to invalid. Now that we have our keyboard event class, we can work on our keyboard implementation. Let's go ahead and generate these definitions. I'm going to go ahead and add underscores to the end of all of the definition parameters. For checking if a key is pressed, we will just check in our array whether that value is true or false and return it. For checking if the event buffer is empty, we will just call the empty function from our queue. For reading an event, what we will do is we will say, if the event buffer is empty, we'll generate that invalid keyboard event and return it with the default constructor. Otherwise, we are going to get the event at the front of the buffer, remove it by popping it from the queue, and then we are going to return it. Next is the onWindows keyboard message, which this is going to be called from the window proc function in our window class. So what we're going to do is we're going to create a keyboard event and pass in the message, the W param and the L param. We're going to have a switch case on the keyboard event's type. If it's a key down, then we are going to assign the key states at whatever that key code is to be true. If it's key up, we'll set it to false. And then if it's a character, we don't care. We're not going to do anything with that. After we've set the key state, we are just going to push this keyboard event into our queue. And then we are done with the keyboard class. Before we implement the mouse class, we can go ahead and add in the logic into our window proc callback in our window class. So let's go ahead and do that. Our window proc callback is going to be very simple. All we are going to do is we're going to have a switch on the message, and if it is any of the keyboard messages, we will call the onWindows keyboard message function from our keyboard class and just pass in the message and the parameters. If it is not a keyboard message, we're just going to call the default window proc callback. Next, we need to work on the mouse implementation, so let's go to that. Our mouse class will look like this. We have a similar setup to the keyboard class, where the window class is a friend of the mouse class, and that is just so the window proc callback is able to access the onWindows mouse message function in the mouse class. We are going to have getters for getting the X position, the Y position, or just getting both as a mouse point. We'll have functions just for working with the event buffer to check if it's empty or to read an event. We'll have a queue of mouse events, and then we'll store the current X and Y position. One other thing is we'll also have the last press button. So depending on if this was the left mouse button or the right mouse button or middle mouse button, we will store that in the last press button. And whenever a button is released, that'll be reset to none. I'll explain why I'm doing this when we implement the onWindows mouse message function. We'll need to create the mouse point struct in the mouse event class before we can finish the mouse class. So let's go ahead and do that. We're going to create a header for the mouse point. The mouse point's just a struct with an integer for X and Y. And now let's create the header for the mouse event. In the mouse event, we're going to include our precompiled header. We're also going to include the mouse point header. Now let's go ahead and look at the layout for the mouse event class. We're going to store the type in the button, and this is going to be one-to-one comparisons with the Ultralight implementation of the mouse event type and mouse event button enumerators. We are going to have the default constructor, which will create an invalid mouse event, and then we are going to have the constructor that we expect where we pass in the message and the parameters from our window proc callback. Just like the keyboard event, we'll have functions for checking if it's valid, getting the type, as well as getting the button. We will also have getters for getting the position and getting the X and Y position individually, as well as converting this mouse event to an Ultralight mouse event. The only members we will have to store for this is the type, the button, and then the X and Y position. We are not storing the parameters like we were for the keyboard event because we are not going to be calling a constructor that allows us to pass those in. Let's generate the definitions for these functions. First, I'm just going to fix the function definition parameters to end with underscores. The default constructor will generate an invalid event, so I'll go ahead and put that in where the type is uninitialized, the button is uninitialized, and the X and Y are set to 0. For the constructor where we are passing in the parameters, it will look like this, where we are extracting the X and Y from the low word and high word from our L param. And then we're going to have a switch case on the message passed in, and should be pretty self-explanatory. We just have all of our mouse events, and we are determining the button and type based off of that. For checking if it is valid, we will just make sure that the type and button are both not uninitialized. For getting the type, just return type, button, we will return button. For pose, we will return the mouse point. For get pose X, we will return the X, and get pose Y, we will return the Y. Now is the part where we need to convert this to an Ultralight mouse event. What we will do is we will declare an Ultralight mouse event, and then we will set the button and type by doing a static cast from our button and type, which should be a one-to-one comparison. Then we will just assign the X and Y, and then return the mouse event. One thing you may have noticed is that we do not have a one-to-one comparison for raw mouse movement. And that is because there is no mouse event type for a raw mouse move in Ultralight. So for any mouse events we have that are raw mouse moves, we will not be passing them into our Ultralight views. Now that our mouse event class is done, we can work on the implementation for our mouse class. Let's go ahead and include our mouse event header, and then we can generate the definitions for all of this. As usual, I'm going to fix the function definitions to have underscores, and now we can begin defining these. So get pose X will return the X, Y will return the Y, get pose will return a mouse point. For checking if the event buffer is empty, we will just call the empty function. When we read an event, if it is empty, we will return an invalid event. Otherwise, we'll get the one from the front of the queue, pop it from the queue, and then return it. I had mentioned before that we are going to be storing the last press button. The reason for this is because we need to know what button was last pressed to be passed in with mouse moves to Ultralight. This could be used for lots of things, including highlighting text, since you need to know if the mouse is pressed on a mouse move in order to trigger a text highlight. Because of that, what we are going to do is on any mouse down event, we are going to assign the last press button, and on any mouse up event, we are going to reset it to none. And then on a mouse move event, we are going to override the button to be the last press button. So if there is no button pressed, then the button will be assigned to none, and if there is one pressed, then it will be passed in with the mouse move when we convert it to an Ultralight event. The last thing we're going to do is just push this into our event buffer, and now our mouse class is complete. Let's go back to our window proc callback and implement the mouse messages. What we are going to do for these is on mouse move, we just pass in the message. If a button is pressed, we are going to pass in the mouse message as well as set capture. The purpose of set capture is it will allow us to Move the mouse off of the window and keep capturing input until we release capture. When a button is released, we are going to pass the message in, and then we are going to call release capture so that we don't keep capturing messages when the mouse is off the window and we've released the button. We are now complete with our window and input implementation, so we need to add this to our engine class. Inside of our engine header, let's include the window header. And then let's go back to our initialize function in the engine. We want to initialize the window, so we will just say, if the window is not initialized, return false. Then we want to assign the mouse and keyboard pointers from the window instance, so we will just do that with getMouse and getKeyboard. For our engine tick, we will need to process the Windows messages first, so we will call process messages. And if you remember, process messages will return false if the window is closed. So if that happens, we will assign isRunning to false and then return out of tick early. Next, for processing the mouse messages, we are just going to have a while loop while the event buffer is not empty. We are going to read in the next event, and then we could process it here. For processing the keyboard messages, it is the same idea, where we check if the event buffer is empty for the keyboard, and if it's not, then we get the next keyboard event. Now we just need to add in creating our engine class and our main loop and our source CPP. So what we will do here is we will create an engine instance. We will initialize it to 1600 by 900 with the title window title. We will create a timer because we need to be able to pass in the delta time to our tick function. Then we're going to start the timer and then have a while loop for while the engine is still running, calculate the delta time, restart the timer, and then call the engine tick function and pass in the delta time. Now if we run this program, we should just have a window. Oh, and actually the window instantly closed because after we initialize the window, we need to assign isRunning to true. So now if we run this, all right, we have our window and it does not instantly close. If we wanted to extract information about our keyboard event, we could do something like this, where we check if the keyboard event is valid and then build a string based off of the type and then the key code, and then just output it to our console, and that would look like this. If I'm pressing A, I get the character 97 because it's lowercase a, but the key down and key up are 65, which is the capital A ASCII code. We could do something similar for the mouse event, where we build a string based off of the button that is pressed, and then the mouse event's type, and just print that out. And you can see when I'm moving the mouse, we get mouse moves. If I have the mouse down, we get a mouse down. If I hold down the mouse when I move my mouse, it is also applied to the mouse move. Now that our Windows and Input section is complete, the next thing to begin working on is our renderer section. Let's create a folder called Graphics and create our renderer header. Our renderer class layout will look like this, and before we get into this, there's a couple things I want to add to the precompiled header. Let's go ahead and open that up. We're going to add the D3D11 header, the DirectX Math header, the D3D compiler, the WRL client header for using COM pointers, and then the vector header. Let's go back to our renderer header. We'll have to define all of the other parts of the renderer before we can actually define the renderer's implementation. So let's start off with the D3D class. We're going to create a new folder for all of the DirectX related things, and we'll call this D3D. And then we can make our D3D class header. We will include the precompiled header, and our D3D class will look like this. Now, in the UML diagram, I had two extra functions for getting the width and height associated with the swap chain for the D3D class, but I realized later that I didn't actually need that, so I've removed it in this. Let's generate the definitions for these functions. I'm not going to go into as much detail for describing the DirectX 11 implementation because it's all just basic DirectX 11 things. I'm not doing anything fancy here. We're just going to have a function for initializing where we pass in the window pointer, and then that initialize function will call all of our other initialize functions. So we'll have initialize device and swap chain, initialize render target, initialize depth stencil buffer and state, initialize rasterizer state, and then initialize sampler state. We're going to store the handle to the window as well as the width and height for the swap chain. Let's go ahead and look at the initialize function. And for this, we are going to need to include the window header actually. Now we can get the handle to the window and the width and height and store it here. And we will first call initialize device and swap chain. So let's go ahead and do this implementation. We're going to create our swap chain description. The width and height of the swap chain will match our window's width and height. We're setting the refresh rate to be 60 Hertz, but it doesn't really matter, I don't think, because in any windowed application, I believe it will just default to your monitor's refresh rate. And I don't think anybody really uses the full screen mode anymore in modern apps. I think they just use a borderless window that takes up the full screen. For the format, we are using 8 bits for our red, green, blue, and alpha values. We're not doing anything with the scanline ordering and scaling. We're just leaving it as unspecified. For our sample count, we are not going to be doing multi-sampled anti-aliasing until later to compare the difference in how it looks. So we'll just have a sample count of 1, and for the quality, we'll have 0, of course. For the buffer usage, this is just render target output. And then for the buffer count, we're only setting it to 1 because this will be double buffered by default in windowed mode. If we were using the full screen mode, we would, I guess, set this to 2 to have double buffering. For the output window, we're just storing the handle to our window. And then, of course, we're setting window to true. For a swap effect, just what you'd expect, swap effect discard. And then for our flags, I have it for swap chain flag allow mode switch, but I guess I don't really need this because I'm not going to be switching into the full screen mode, but I'll just leave it there because it doesn't really matter. We're going to declare a variable to store the result from when we call create device and swap chain. We're just going to default to whatever the first adapter we find is. So I'm just passing a null pointer. Of course, we're using a hardware driver. We're not using a software driver, so we'll just pass in 0 for the third parameter. I'm going to enable the debug layers in case anything blows up so we can see it in the output window. We're just using the defaults for the feature levels and number of feature levels. And then we are getting back our swap chain, our device, and our device context. If that fails, we'll call the return false if fail macro, where we pass in our result from that function call, and then the error that we want to pop up if it fails. Now for that, we have to include the error logger header in our utility section. So back at the top, we'll add that include. And actually, I'm going to put that in the precompiled header instead of here. So we'll go up here. And we will just have that in the precompiled header. Back in the D3D class, let's see. All right, so now there's no error there. That is perfectly fine. Now for our initialize render target, we are going to create a COM pointer for a 2D texture. We are going to get the texture buffer from our swap chain. And then, of course, that's going to be the back buffer. And then we are going to create our render target view with that texture. If either of these fail, we'll call the return false if fail macro. And then we have a detailed message of what failed. Next, let's look at the initialize depth stencil buffer and state. We're going to initialize a depth stencil. In the description, we'll specify that it has 24 bits for the depth, then 8 bits for the stencil. The width and height will match the width and height of our swap chain and window. For our MEP levels, we'll just use 1. For our bind flags, it is a depth stencil, so we'll use bind depth stencil. We are not going to have multi-sampled anti-aliasing right now, so we'll have a sample count of 1 with a quality of 0. We need to create the texture for the depth stencil buffer, and then we need to create the view for the depth stencil. Lastly, we need to create the depth stencil state, and for the comparison function, we're just going to use less than or equal to get the normal expected behavior. Next, let's look at initialize rasterizer state, and in here we're just going to use the default rasterizer state, and we're just going to set the cull mode to none. By default, multi-sampled anti-aliasing are disabled, so we don't have to assign anything there when using this CD3D11 struct. And then we're going to create the rasterizer state. Of course, if it fails, we will return false. Otherwise, we will return true. Lastly, we are going to be initializing the sampler state. We're just going to create our description where we are using clamping for a UV and W texture coordinates in case they go outside of the boundaries. We're just going to be using point sampling, and that concludes our D3D class. So let's go back to our render. Next, we are going to make our ConstantBuffer. So we'll just make a new header. This is going to be similar to the one that we did in the tutorials. We will include our precompiled header, and the layout will look like this. And we're actually going to do the implementation in a CPP file. So let's add a new CPP file. And it is going to look like this. So we'll have get, where we just call get on our com pointer for our buffer. We're going to have get address of, just to access get address of from the com pointer. When we initialize, we're passing in a pointer to the device and a pointer to the device context. And then we are storing the device context pointer. And then we are using the device's pointer to actually create this constant buffer. We'll need to be able to map and unmap, so we'll have the D3D11 CPU access write flags for our CPU access flags. And we are going to be having this as dynamic because of the fact that we need to be able to map and unmap and update it. For the byte width, this is just a way that we can make sure that it is aligned to 16 bytes. When we need to actually update the constant buffer, we can just call apply changes. And what that's going to do is it's going to map to the constant buffer, and then it's going to call copy memory and copy over whatever is in our data object, and then is going to unmap from the constant buffer. For all the types that we will want to use for our constant buffers, here is where we would declare them. So currently it's just going to be for a matrix, but whenever we add more types for our constant buffers, we would just add them here. Next, let's take a look at our shaders. So we'll create a new directory for this, call it shaders, and we're going to have a PixelShader. Our PixelShader will look like this. We'll just have an initialize, get shader, get buffer, and then we're going to be storing com pointers to our shader and then the shader buffer. Let's create the CPP file. And the implementation for the PixelShader will look like so. When we pass in a file, we're just going to be looking at the executables directory since the compiled shader objects are going to be in the same directory as our executable. And then we're just going to be appending the path that we pass in. Now, we actually are going to add the directory helper header into our precompiled header so that we can access that. So we are resolving the file path, we're reading it into our file blob, and then we are creating the PixelShader from the file blob. For get shader, we are just calling get on the shader object, and then for get buffer, we are calling get on the shader buffer object. The VertexShader class will be pretty similar. Let's go ahead and create the header for this. One difference, however, is when we are initializing the VertexShader, we're going to have it set up where the VertexShader will also store the input layout associated with this VertexShader. So when we initialize it, we'll be expected to pass in the vector of the input element descriptions associated with this input layout, and then we'll be able to call get input layout to retrieve that whenever we are binding the stages for our pipeline. Let's create the CPP file for the implementation. So just like with the PixelShader, we're getting the executable directory, we're reading it to a blob, and then we're calling create VertexShader. Same idea, we pass in the buffer pointer, buffer size, and we're storing it in our shader object. And then we are creating the input layout with whatever was passed in for the layout description. Then we will just have our getShader, getBuffer, and getInputLayout functions. Now let's go back to our renderer, and we should be able to set up a lot of this. But first, we need to add some includes up here. Now we won't be able to implement render view until our Ultralight implementation is complete, so I'm just going to comment that out for now. And I'm going to generate the definitions for the rest of these. For our renderer initialize, what we are going to do is we're going to store the pointer to the window, and then we are going to attempt to initialize our D3D class instance. If it fails, of course, we'll return false. Then we attempt to call initialize constant buffers and then initialize shaders. So we need to implement these. So let's go ahead and go down to initialize constant buffers. We're going to have two constant buffers, one for the world matrix and then one for the orthographic matrix. When we create the orthographic matrix, we are calling the getWidth and getHeight functions from our window class. So we need to include our window header. So what we're doing is we're initializing the orthographic matrix. We're passing in the pointer for our D3D device and D3D device context. After that, we're assigning the data, which is going to be a matrix, to an orthographic matrix. And we are using the XM matrix orthographic off-center LH. We have this set up in a way where the top left coordinate of the window will be 0 for our X and 0 for our Y. And then the bottom right of the window will be our window's width for the X and the window's height for the Y. So if we're using 1600 by 900 for our window's resolution, then the bottom right of the window's coordinate will be 1600 for the X and then 900 for the Y. Next, we are just updating the constant buffer, and then, of course, we are making sure that it was successful, so we return false if that fails. After that, we are initializing the constant buffer for the world matrix, which I'd called it the quad world matrix, because really, when we render these HTML views, we're just going to be rendering them to a quad. So that's why I'd called it that here. When we are assigning the matrix for the world matrix, for now, I'm just assigning it to a scaling matrix, which will scale it to have the same width as the window and the same height as the window. And of course, the Z is unaffected, so we're just passing in 1 for the Z scaling. Then we are applying the changes there. After we call initialize constant buffers, we call initialize shaders. Now, in order to initialize our shaders, we have to have some shaders in our program. So let's go ahead and add a new folder for our HLSL shaders. And I'm going to try to pull this out of here. There we go. We're going to have a section for our pixel shaders, a section for our vertex shaders. Now we have to create the vertex shader. So create this, and I'm going to call it VS 3PF 2TF HLSL. So what this means is it's a vertex shader. Our first input is going to be 3 positions, and they're going to be floats. Then after that, we're going to have 2 texture floats. That's all we'll need. So create this. Before we put in any shader code, we need to make sure that it's set up properly in our solution. So we'll right click, we'll go to properties, make sure all configurations is selected. For our HLSL compiler, we're going to be using shader model 5. And then for the shader type, this is a vertex shader. We'll press OK. For this vertex shader, the first thing is we are packing our matrices to be row major. In this way, we do not have to transpose them before we bind them to the pipeline. We're going to have our first constant buffer be the orthographic matrix, and then our second constant buffer is going to be the world matrix. For our input, just like we said before, our first 3 are going to be for our position. They're going to be floats. And then we are going to have 2 floats for our texture coordinates. For the output, we're just having a float 4 for the position, and then a float 2 for the text coord, because we're also going to be storing the W in the position when we pass it out. Shader is pretty simple. We are just multiplying the position by whatever our world view projection matrix is, which in this case, it's an ortho matrix, not a view projection matrix necessarily, but I assume they're called the same thing. And then our text coordinates aren't being transformed, and then we are just returning these, and then that'll be passed on to the PixelShader. Next, let's take a look at the PixelShader. Now, the PixelShader will be expecting 4 floats for the position, so I'll have 4 PF, and then 2 floats for the texture coordinate, so I'll have 2 TF there. Let's go ahead and set up the properties before we do anything. We'll have to have shader model 5, and then for the shader type, it is a pixel shader. Our pixel shader for now will look like this. We're going to modify it later to account for gamma correction, but for now we are not going to do that yet, just so that we can see the difference later on. It's nothing fancy, just a typical pixel shader where we are sampling whatever the texture object is that is bound. Now that we have our shaders created inside of our renderer class, we can define the implementation for our initialize shaders function. All we are going to do is, for our pixel shader object, we're going to call initialize, and then we are going to pass in the D3D device pointer and the pixel shader's path. For the vertex shader, same idea. We're going to initialize it, pass in the pointer to the device, the path to the vertex shader, but we also need to pass in the input layout description for this vertex shader. What I'm going to do actually is inside of our D3D directory, I'm going to create a new directory just to store our input layouts. So our input layout for the shader that we just created, we're going to have 3 32-bit floats for our position, and then we are going to have 2 32-bit floats for our texture coordinate. We're not going to have any instancing or anything, so this is all just per vertex data. Now if we go back to our renderer class, we just need to include the header for that input layout description. And now we don't have any error there. Next, let's look at our other functions to implement. For get D3D pointer, all we're doing is just returning the address of our D3D class instance. For end frame, we're just going to present our frame by calling present from the swap chain. For begin frame, we are first going to clear the state for our new frame, and then we are going to call set render targets and pass in the render target view and the def stencil view for this render target. We're going to set the def stencil state, set the primitive topology to the triangle list, which is all we're going to be using for this. We're going to just create a viewport here that has the dimensions of our window. For our rasterizer state, we will set the viewport, and then we will set the rasterizer state. For our pixel shader, we're going to set the sampler to be the sampler state that we created in the D3D class. We're going to clear the background color to just be black. So that's why we have this background color array of floats. And then we're going to call clear render target view, where we pass in the background color to our render target view. And then we're going to call clear depth stencil view, where we clear the depth and the stencil values. We're going to clear the depth to be 1.0 and the stencil values to be 0. Now we are almost done with our renderer section. We still need to do the vertex buffer, but we're going to come right back to that. First, let's go back to our engine class and implement the render function as well as our renderer class here. So first, we need to include the renderer header. We need to generate the render definition. And before we look at the renderer definition, let's go to our initialize function because we still need to initialize the renderer. If the renderer fails to initialize, we'll return false. Let's go down to the render function. All we are going to do is call begin frame and then call end frame. Now if we test this, we should just get a black window. And we actually did not get a black window because in our source CPP, we still need to call render. Now if we run this, we should just get a black window. All right, perfect. So next what we need to do is we're going to implement the VertexBuffer class template, and then we are going to just draw a quad on the screen, and then we will be done with our renderer section. Up in our D3D section, we will create a new item. This is going to be for our VertexBuffer. And what we're going to do is we're actually going to have another header that stores our vertex types. It is going to be called Vertex. So we'll include the precompiled header in this one. And for now, the only vertex type that we'll have is the one that we're expecting in our VertexShader, where we have 3 floats for position and 2 floats for the texture. Now let's go back to our VertexBuffer header, and we need to include this vertex header. We don't necessarily need to. We are going to be storing our vertex data in this storage object, and then we are going to be storing the stride so that we can just call stride pointer whenever we go to actually draw an object that uses this vertex buffer. Let's go ahead and create the CPP file. So we're just going to have get to get our buffer, get address of, access the get address of function from the com pointer, vertex count, which is just going to get the size from our vector of vertices that we have stored. Stride will get to stride pointer will return the address of the stride. Initialize will take in our device pointer and then our vector of vertices. Of course, if the vector of vertices is blank, we'll just return fail because it doesn't make sense. Otherwise, we are going to create a buffer. For the byte width, we'll just take the stride and multiply it by however many vertices there are. For the bind flags, it's a vertex buffer. We are not going to dynamically update our vertex buffer, or at least it's not set up to be. So the CPU access flags will be 0 and the usage will be default here. Of course, if you wanted to be able to dynamically update it, that would not be difficult to change. Then we are just assigning what the default data is with this D3D11 subresource data struct, and then we are just calling create buffer. The last thing is we need to declare all of the data types that we'll be using this template, so that's why we have this vertex 3pf 2tf right here. Now let's go back to our renderer class. We need to include our new header. Something I did on accident was I accidentally put the vertex buffer and vertex files inside of our shader directory, but these should actually be in the D3D directory. I'll go ahead and move those. And then back in our renderer header, we will include these. Next, for now, we are going to declare an object right here just to store the vertex buffer. And this is going to hold the vertices for our quad to make sure everything's working as expected. Inside of our initialize, we can just go ahead and initialize this after the shaders. So the way that we will do this is we'll just initialize a vertex buffer with 2 triangles to make up a quad. The top left point will be 0, 0, and the bottom right point will be 1, 1. So we'll have a unit length of exactly 1. We will just initialize the quad here. For now, we're just going to create a temporary render quad function. The way that this will look is we are going to bind our vertex shader, bind the pixel shader, bind both of our constant buffers, the orthographic matrix to the first slot and the world matrix to the second slot. We're going to set the input layout for the input assembler to be the input layout from our vertex shader. Then we are going to set the input assembler's vertex buffer to be our quad vertex buffer. And then we're just going to call draw. We're going to pass in 6 vertices since our quad has 6 vertices. Next, we need to make sure that our engine is actually attempting to render this quad. And if we run it now, we won't get expected results. And the reason we are not seeing anything here is because inside of our pixel shader, we are sampling from the texture. Now, in the end, here, we will be sampling from the texture that holds the texture for our HTML view. But since we don't currently have the Ultralight implementation in place, we're just going to change this to temporarily return a flat color. So I'm just going to return red. I have 1 for the red value, 0 for the green and blue, and then 1 for the alpha. And perfect. That's exactly what we would expect. Let's say that we just wanted to cover the top left 25% of the screen. We could go back to the renderer CPP, where we are initializing the constant buffers, and change this to be width divided by 2, height divided by 2 for the world matrix. And now it should just be the top left quarter of the screen. And of course, if you wanted to move this around, you would just multiply it by a translation matrix after you scale it. That concludes the renderer section of our demo. Now the last thing that we need to do is the Ultralight implementation. Let's go ahead and create a new directory for our Ultralight implementation. The first header we're going to make is for the HtmlViewManager. For the HtmlViewManager class, we're going to need the HtmlView. So let's just go ahead and create that header. And we can also just declare the class. Let's go back to the HtmlViewManager. For our HtmlViewManager, we'll need to add a few headers into our precompiled header. Let's go ahead and go to this. The first header we'll add is our Ultralight header. We are also going to add the memory header so that we can use shared pointers and unique pointers, the fstream header for input file streams, and then the map header so that we can use maps. Let's go back into the HtmlViewManager header, and it's going to look like this. So we'll need access to our mouse event and keyboard event classes for when we need to fire a mouse or keyboard event to the views that exist. We'll need access to the D3D class so that we can hold a pointer to our D3D class instance. We'll need access to the VertexBuffer because currently inside of our renderer, we are storing that VertexBuffer for our quad. However, we are going to move this to store that inside of our HtmlViewManager so that the renderer does not have to hold this, since that quad is specifically meant for the HTML views. For our functions in the HtmlViewManager, we're going to have initialize, where we initialize our Ultralight instance. Update views is going to update the render target, which will also update the texture for each view. We'll call this once per frame before we render the frame. Create view is just what we're going to call to create a new view. Get views is just to get all of our views for when we render them. You'll see that we have a ref pointer to the Ultralight renderer object, and that is just because that's how we're supposed to store it, and when we try to create the Ultralight renderer, it will return a ref pointer. We have unique pointers for the logger, FontLoader, file system, and GPU driver implementations, which we haven't done these yet. For now, I'm just going to comment these out. We'll have a vector of shared pointers for our HTML views, and then of course, like we just discussed, we'll have the VertexBuffer. So let's begin on the implementation. I'm going to create all of these definitions. So first off, for our initialize function, we want to store the pointer to the D3D class, and then we want to initialize Ultralight. So to create the Ultralight renderer, we'll call renderer create, and then we'll store that in Ultralight renderer, and as long as it's not a null pointer, we are going to return true. There's a lot more we have to do in regards to initializing our Ultralight renderer, but we'll come back to that in just a moment. Let's take a look at what else we can go ahead and do. So for our destructor, we are going to assign the Ultralight renderer back to null pointer. We should only call the destructor on the HtmlViewManager when this program closes, so we'll no longer be using anything at that point. For getting our views, we're going to return that vector of shared pointers of HTML views. For create view, we are going to call create view from our Ultralight renderer, and we are passing in the width, height is transparent. And then for the last argument, the session, which we're not using the session, so we're just using null pointer. I believe there is a default session that we'll use when you pass in null pointer instead of a unique session. If it fails to create, we're just returning null pointer, Otherwise, if it's successful, this is where we would create the HTML view and add it to our vector, and then return the shared pointer. Of course, this is not yet implemented, so I'm just going to comment that out. And for now, this would just return null pointer no matter what. And it might seem strange that I went ahead and did this, but it will make sense very shortly. Inside of our engine, let's go ahead and initialize Ultralight and try to create a view and see what happens. So we'll uncomment out the HtmlViewManager part. We need to add our include. Let's go to our initialize function where we will initialize it. All we are doing here is we are calling initialize on the HtmlViewManager. If it fails, we're logging a critical error. And then we are creating a view for the HtmlViewManager. And if that fails, we're logging a critical error. Let's go ahead and run this and see what happens. Okay, so it triggered a breakpoint on create view. If we go back into our engine CPP, that means that it must have successfully initialized Ultralight, but it failed on create view. So what's happening here is an error is occurring when we try to create the view, and what it will do is it will pass that error into our logger that we have implemented. Of course, we have not implemented a logger, so let's go ahead and do that and see what it's saying. We're going to make a new directory called LoggerAdapters. Create a header for our LoggerDefault class. The logger will be pretty basic. We just create a class that inherits from the Ultralight logger class. So we'll do an F12 on this. It only has one function, log message, and we're going to be overriding this and just doing something with the message. We'll just have a message box come up. So if we go back, let's go ahead and create the CPP file. What we will do is, depending on how severe the error is, so if it's an error or if it's a warning, then we're just going to log critical error with error handler, which, keep in mind, when we call log critical error, we are just having a message box come up. If we want the program to actually close, I guess we would call log fatal error. This passes in an Ultralight string 16, so we can convert that to just a normal string by doing .utf8 on it after converting it to an Ultralight string, and then doing .data, and that'll give us a char pointer, which log critical error expects a string, so we can pass in a char pointer to that, no problem. Now we need to tell Ultralight to use this logger that we've created. So we'll go back to the HtmlViewManager. We need to add this include. Now let's go into where we were initializing the view manager. We're going to call makeUnique to create our logger instance. And then we need to make sure that we set up Ultralight to use our logger. So what we'll do is there's a singleton for the Ultralight platform. We can get the instance by calling the instance function on this singleton, and then we can call setLogger and pass in the pointer to our logger to set the logger that will be used. Now let's run this again and see what we get. Okay, so we get an error that comes up. It says we tried to create a view, but the font loader was null. So we need to create a font loader. Let's go ahead and implement the font loader. We'll create a new directory for the font loader adapters. The font loader implementation is a bit more complex. On the app core repository, there is a font loader we can use for the Windows platform. And this font loader is also using this text analysis source header and CPP file. So what I'm going to do is I'm just going to pretty much copy and paste these, and we are going to use the implementation inside of the app core repository. First, we will create the FontLoaderWin header. And then we will create the CPP. Next, we will create the text analysis source header. And now for the text analysis source CPP. Now that these are implemented, we can go back into our HtmlViewManager and add this include. Now we can uncomment our unique pointer for the font loader and go into our initialize function. We will want to create our font loader with make unique, and then we will want to set our Ultralight instance to be using this font loader. So now let's run this again and see what we get. Okay, now we get failed to create HtmlView, which it didn't actually fail to create the HtmlView, because if you remember, our createView function returns null pointer no matter what. So that error was actually being reported right here in our engine CPP, where we were checking if it was null pointer. Our Ultralight renderer createView function was actually successful though. That being said, there's still a lot more we have to implement here. We'll want to implement a file system to be used, and then the GPU driver is going to be the big part of this. Let's go ahead and implement the file system. We'll create a new header for the FileSystemDefault class. It's going to look like this, so we'll just have functions for if a file exists, getting the file size, getting the file's MIME type, opening the file, closing the file, reading from file, and then getting the relative path. The code I'm going to use is very similar for the Linux implementation on the Ultralight App Core repository. There's also a Windows-specific implementation, but I found that it seemed a little more complicated than it needed to be, and I didn't want to use a bunch of functions that I'm not familiar with. One thing to note is that these functions are expecting file handles for the first argument for a lot of them, and this is really just an integer. It's technically a size t, but that's just an integer. It is important to keep in mind because we're going to have a map where we have our file handle for the key, and then it is going to be holding a unique pointer to an input file stream. I have this file system set up where we store the base directory of wherever we want this file system to be at. And in this case, if they pass in a blank, we're going to default to the executables directory. Let's go ahead and create the CPP file and take a look at what this code will look like. So at the top for our constructor, if the base directory is not blank, then we'll use whatever they pass in. Otherwise, we're just going to get the executables directory with our directory helper utility class. For the destructor, we're not doing anything. We're checking if a file exists. We're just creating an input file stream object, and we are getting the path. Notice that we're calling getRelativePath. What this is doing is it's taking our base directory and appending on this other directory. For getFileSize, we are just taking an open file. We are seeking to the end of it, and we are calling telg to see how many bytes are in that file. For getFileMIME we are going to be determining the extension for the file, so that could be something like PNG or JPG. And then we are going to be calling file extension to MIME type from our MIME type helper utility class. For open file, we're just creating an input file stream. We are opening the file, and then if we don't successfully open it, we're returning invalid file handle. Otherwise, if we do successfully open it, then inside of our maps, we are creating a new entry for this file, and then we are just storing the unique pointer for that input file stream inside of our map. For close file, we are just removing this file handle from our map, and then reassigning that handle to be invalid file handle. For read from file, we are just seeking to the beginning of an open file, and then reading the number of bytes, and then returning however many bytes were read. And then for getRelativePath, which was called before in this code, it is just building the path based off of the base directory and whatever path was passed in. Now let's go ahead and change our HtmlViewManager to use this file system. So we'll uncomment that. We need to add the include. Now we need to go into our initialize function, set this up to use our file system. We will just call make unique on the file system, and then on our Ultralight platform instance, we will call set file system. Now that our file system is set up, the next thing we're going to do is work on our GPU driver adapter. we'll create a new directory called GPU adapters. In the Ultralight app core repository, they have a class for the GPU driver implementation, and that class will inherit from the GPU driver. Every single different implementation will have a different class that inherits from the GPU driver implementation and overrides certain functionality. Since we are only focused on the Windows platform, we could technically just have one class for the GPU driver. However, I want to follow a similar pattern to what they have because for some of the functions we are overriding, we are pretty much just going to be copying and pasting the functionality that the GPU driver implementation class has. We're not going to do it exactly the same, but it's going to be pretty similar. Let's go ahead and create a new header file for the GPU driver implementation class. Our GPU driver implementation class will look like this. Notice that there are these functions that we are overriding in the GPU driver implementation. However, if we go to the GPU driver class that we are inheriting from, there are actually more functions here that we are not overriding. So these will be overridden in our actual GPU driver class. We also have these functions draw geometry and clear render buffer. These two functions will also be overridden inside of the GPU driver class. Let's go ahead and generate these definitions. For getting the next texture ID, we're just going to increment our next texture ID variable and return that. The same idea applies for next render buffer ID as well as next geometry ID. For update command list, this is the same as what the GPU driver implementation does on the app core repository, so we are just going to see that there is at least one thing in this list. And then if it is, we are resizing a command list vector that we have, and then we are copying all the commands into our command list. For drawing the command list, if the command list is not empty, we are going to go through each command, and we can either have a command to draw something or a command to clear a render buffer. If we are drawing something, we'll call draw geometry, and if we are clearing the render buffer, we will just call clear render buffer. Draw geometry will be overridden and defined in our GPU driver D3D11 class, as well as clear render buffer. Let's go ahead and create our GPU driver D3D11 class. Our GPU driver D3D11 class will look like this. Now, before we go through everything, one thing to note is we have these functions like create texture, update texture, create render buffer, create geometry, and the first argument of all of these takes in either a texture ID, a render buffer ID, or a geometry ID. If we go to the bottom of our class, we'll see that we are going to have a map of all of our geometry entries, all of our render target entries, and all of our texture entries. We need to go ahead and define the layout of these entries. So let's create a new header, and it's just going to have all of these in it. It's going to be called map entry. Our map entry header will look like this. We're just having a using here at the beginning so we can use com pointer instead of typing out Microsoft WRL com pointer. For our geometry entry, our first variable is an enumerator from Ultralight that will be the VertexBuffer's format. The VertexBuffer format will be one of two formats. The VertexBuffer format will determine which VertexShader and PixelShader is used when Ultralight draws geometry. Next, for every geometry entry, we're just going to have a VertexBuffer to store all the vertices, and then an index buffer to store all the indices. For every texture entry, we're going to have a texture for the texture, and then a shader resource view for that texture shader resource view. We'll have booleans to store if it is a multi-sampled anti-alias render target, and then a boolean to store if it needs resolve. So if this is a multi-sampled anti-alias render target, then we will need to resolve the textures. So we will also store a texture for the resolved texture and a shader resource view for the resolved shader resource view. For our render target entry, we're just going to have a render target view, and then we are going to have the ID of the texture associated with this render target entry. So inside of our map, for our texture entries, One of those textures will be for this render target, and the ID inside of that map will match the render target texture ID inside of the render target entry. Let's go back to our GPU driver header, and let's just review the functions that we have. For our constructor, we need to pass in the D3D class pointer, and we are going to store that inside of this class so that we can access our device and our device context and all of that. We will have functions to create a texture, update a texture, and destroy a texture, create a render buffer, destroy a render buffer, create a geometry entry, update that geometry entry, and then destroy it. We will need to implement how to draw geometry as well as how to clear the render buffer. Another function we have that was not a part of the Ultralight implementation that I put in is a way to get the address of a shader resource view. Later, when we need to actually bind this to our PixelShader to be able to sample from it and draw it to a quad, we need to be able to get the address of the shader resource view for that texture. We're going to have initialization functions for loading the shaders, initializing the sampler states used, the blend states used, the rasterizer states. We will need a way to bind a render buffer, set a viewport, bind a texture, update a ConstantBuffer, bind geometry, and then apply a projection. We will, of course, have our 3 maps. We will have 2 different vertex shaders and 2 different pixel shaders, and which one we use will be determined by the VertexBuffer format that we discussed earlier. We will have 1 ConstantBuffer for Ultralight. We will just store that in a variable called ConstantBuffer, and then we will just store our sampler states, our blend states, and our rasterizer states. We need to define the ConstantBuffer type. So what we're going to do is inside of D3D, we are going to create a new header for our ConstantBuffer types. And it is going to look like this for the Ultralight ConstantBuffer. In case you're wondering where I got this from, this is coming from the GPU driver D3D11 CBP in the app core repository. Now let's go into our ConstantBuffer and just include this header. And then inside of our CPP, we need to declare that we're actually going to use this. Let's go back to our GPU driver class. And now we should have no error for that. Let's go ahead and begin the implementation. So we will create all of our definitions. For our constructor, we are going to begin by storing the pointer to our D3D class instance. Then we are going to load in our pixel and vertex shaders, initialize our sampler states, initialize the blend states, the rasterizer states, and then we will attempt to initialize our ConstantBuffer. If anything fails in our initialization, it will result in a fatal error, so the application will be closed. Let's take a look at our load shaders implementation. And to actually implement this, we need to have our Ultralight shaders in our project. So what we will do is inside of our HLSL directory, we will create a new directory for our Ultralight shaders. The shader code is going to be directly ripped from the app core repository from the VS and PS directories. We're going to just copy and paste these 2 shaders from the repository. Now we have to go through and edit the properties for these. So for all of the ones in PS, these are for pixel shaders. And all of the ones with VS are for vertex shaders. Now let's go back to our GPU driver. The way it'll work is we're going to have a path called the fill path. And then we'll also have a path that's called the fill. So if we're doing the fill path, then the vertex shader we'll be using is this one. And if we're just doing a fill, the vertex shader we'll be using is this one. And then the pixel shader name, of course, will either use the fill path pixel shader or the fill pixel shader. Something to note is that for our vertex shaders, we need to have the input layout defined. Let's go back to our input layout descriptions header. For the input layout, Once again, this is just coming from the app core repository, and I'm just copying and pasting it here and renaming it just so I know it's for Ultralight. I need to also include the input layout description header. And now our load shaders is complete. Also note that if any of this fails, we are calling fatal error. Next, we are going to initialize our sampler state. The sampler state we're going to use is the same setup as what was used in the app core repository. Next, we need to initialize our blend states. We will have a blend state for when we have blend enabled and then a blend state for when blend is disabled. What we are doing here yields the same results as what was done in the app core repository. It's just in a bit of less code. Next, we need to create our rasterizer states. So we're going to have a rasterizer state for just when we are rendering normally, and then a rasterizer state for when we have scissoring enabled, if we're only just rendering over a small section. And once again, we are doing this the same way as the repository does it. It's just in a bit less code due to the fact that we're utilizing the creation structs. Next, while we are down here, we can also go ahead and define set viewport. So that's very simple and doesn't really need any explaining. We're just creating a viewport, setting the width and height and the depth, and then on our rasterizer stage, we are setting that viewport. We have now completed the implementation of our constructor. Let's go ahead and look at how we would implement destroying a texture, destroying a render buffer, and destroying a geometry entry. For destroying a texture, all that we would do is we would iterate through our texture map entries and find the texture map entry where the texture ID matches. Once we find it, we would erase it from the texture map, and then we are done. For destroying a render buffer, it's the same idea. We iterate through the render target entries. Once we find it, we reset that render target view, and then we erase the render target entry from the map. For destroying a geometry entry, we'll iterate through the geometry entries. Once we find one, we will reset the vertex buffer and index buffer, and then we will erase them from the map. Next, let's take a look at the create texture function. The first thing we're going to do is make sure that there's not an entry in our texture map that has the same texture ID as the new texture we're trying to create. I don't think this should ever happen, but in case it does, we are calling the fatal error macro. Next, we are verifying that the bitmaps format is valid. There are only two formats that it could possibly be, and if it's not one of these, then we are once again calling the fatal error macro. We are creating a description struct for our 2D texture. We're going to store the width and height from our bitmap. The MIP levels and the array size will both be assigned to 1. For the format, we're going to look at the bitmaps format, and if it's the Ultralight's BGRA8 format, then we are going to use the BHE8RAA8 format. Otherwise, we are just going to use the A8 format. We are defaulting the sample count to 1. Since this texture is meant to be updatable, the usage will be dynamic. Since it's going to be bound as a shader resource, we have the D3D11 bind shader resource flag. And since we are wanting to be able to update it, we have the D3D11 CPU access write flag. Next, we are going to generate this entry in our texture map and retrieve it like so. If the bitmap passed in is empty, that means that we are creating a texture for a render buffer. When this happens, we'll assign the bind flags to be render target and shader resource. The usage will be default, since instead of updating the texture for the render buffer, we will be clearing the render buffer and then rendering to it. And then the CPU access flags will be changed to 0, since once again we don't actually update the render buffer's texture. If multi-sampled anti-aliasing is enabled, then we will use a sample count of 8 and the sample quality of D3D11 standard multi-sample pattern. We will also assign the is multi-sampled anti-alias render target value to true. Lastly, we will attempt to create the texture and store the result in our HR variable. If the bitmap is not empty, then we are creating a texture from the bitmap's data. We will create a struct for our D3D11 sub-resource data. For the pointer to the memory, we will call lock pixels on the bitmap, and that will get us back a pointer to the memory. And then for the pitch, we are looking at the bitmap's bytes per row. And then for the sysmem slice pitch, we are just looking at the bitmap size. Since this is not a 3D texture, the size of the bitmap will be the size for one depth of our texture. Next, we are going to create the texture, store the result in our HR variable, and then we are going to unlock the pixels for that bitmap. If creating the texture for the render target or the bitmap fails, we are going to call the fatal error if fail macro. Next, we need to create a shader resource view so that we can work with the texture. We're just setting the shader resource view's format to be the same as our texture's format. For the view dimension, depending on if this texture entry is a multi-sample anti-alias render target, we will either use the texture 2D multi-sampled format or just the texture 2D format. We're just assigning the MIP levels to 1. And then we are creating the shader resource view, storing the result in HR, and calling the fatal error macro in case it fails. If multi-sampled anti-aliasing is enabled, then what we will do is we will create a resolve texture, and we will store that in the resolve texture variable inside of our texture entry, and then we will create a shader resource view for that resolve texture. Now let's take a look at updating a texture. The implementation for this is pretty much copy and pasted once again from the app core repository. What we are doing is we are getting the texture map entry for this texture ID. If we can't find it for some reason, we will call the fatal error macro, but this should never happen. We are calling map on the entry's texture so that we can update it. If the number of bytes per row matches, then we are just doing a mem copy and calling lock pixels on the bitmap, which will get us back a pointer to the data, and the number of bytes that we are copying is the size of the bitmap. After we're done copying it, we're just calling unlock pixels. If the number of bytes per row does not match, then somehow Ultralight is updating the texture by calling the bitmap create function and then calling the draw bitmap function. Once the texture is updated, we are just calling unmap on it. Next, let's take a look at our create render buffer implementation. First off, the render buffer ID 0 is reserved for the default render target view for our window. We are not going to utilize this, but I guess you could technically render to our render target instead of rendering to these off-screen render targets. We will check if a render target entry exists in our map with the same buffer ID, and if it does, we will call fatal error since we should never have two entries with the same ID. We will find the texture entry that is associated with this render buffer, and if it does not exist, we will call fatal error. We will need to create our render target, so we create the view description. For the format, we're just using 8 bits for blue, green, red, and alpha. Our view dimension is just determined if multi-sampled anti-aliasing is enabled or not. We're going to get the texture from the texture entry, and then we are going to create a new render target entry and get it like so. We will call create render target view, where we pass in the pointer to our texture entry, and then we pass in the address of to our render target view. We're going to store the result in our HR variable so we can check if it fails, and then we are going to store the texture ID inside of the render target texture ID variable for this render target entry. Lastly, we will call the fatal error if fail macro just to make sure that this did not fail. Next, let's take a look at the create geometry function. Just like all of our other create functions, we make sure that there's no entry with the same ID. Next, we will create a new geometry entry variable, and we are setting the format equal to the format of the Ultralight Vertex buffer that's passed in. We're going to create a buffer description for our Vertex buffer. Our Vertex buffers will need to be updatable, so we will use usage dynamic for the usage and CPU access right for our CPU access flags. Since it's a Vertex buffer, the bind flag will just be Vertex buffer, and the byte width will just be whatever the size is of our Ultralight Vertex buffer that is passed in. We'll create a sub-resource data struct to hold the Vertex data, and just get that from our Vertex buffer that's passed in. Next, we'll call create buffer to create this Vertex buffer, and use the Vertex data that's passed in, and store this in our geometry entries Vertex buffer. We need to create the index buffer next, so we'll create the index buffer description. It's exactly the same as the Vertex buffer, except we're using the indices size, and we are using index buffer instead of Vertex buffer for the bind flags. If our index buffer is successfully created, then we'll get down here to where we actually insert this new geometry entry into our geometry map. Let's take a look at updating the geometry. What we'll do is we'll find the entry in our map. Once we find it, we're just going to map the vertex buffer so that we can update the data, do a mem copy, and then unmap it, and then we're going to do the same thing for the index buffer. Next, let's take a look at our draw geometry and clear render buffer functions. For our command list, these are the two functions that will be called. We'll do clear render buffer first since it's easier. So all we are going to do is if the render buffer ID is 0, that's our primary render target view. So we would clear that. I'm not sure why this would ever happen. I don't think it should happen in our implementation, but it's there in case it does. Otherwise, for all of the render buffers associated with Ultralight, we will find it, and then once we find it, we will call clear render target view, and we will pass in our render target, as well as the color we're clearing to, which we are clearing it to black. If multi-sampled anti-aliasing is enabled, then for this texture entry, we will need to assign needs resolved to true. Now let's take a look at drawing the geometry. What we are going to do is first we will bind the render buffer to whatever render buffer we need to bind to. We'll set our viewport to the width and height required by the state that's passed in. Next, we will bind up to 2 textures depending on the texture 1 and 2 IDs in the state. We will update the ConstantBuffer, bind our geometry. We need to make sure that we're using the proper sampler that we created earlier, so we'll call PS set samplers. Depending if this is the fill shader type or the fill path shader type will determine which vertex shaders and which pixel shaders we use. If we have blend enabled, then we will use the blend state enabled that we created. Otherwise, we'll use the blend state where it's disabled. If the scissoring is enabled, then we will use the rasterizer state where scissor is enabled. And then we will set the scissor rex to be the scissor rec that is stored in the state. If scissoring is not enabled, then we will use the default rasterizer state. We need to make sure that we set the pixel shader and vertex shader to both use our constant buffer. And then we will just call draw index with whatever the index count is that's passed in and the index offset. We are getting very close to done with our GPU driver implementation. There's still a few more things we need to implement though. We need to implement binding a render buffer. So when we do this, we want to unbind anything that might have been bound before. So that is why we have this first PixelShader set shader resources call. Next, we are getting our render target for this render buffer. If this is a multi-sampled anti-aliasing render target texture, then we are going to set the needs resolve value to true. And then at the end, we are just going to bind this render target by calling omSetRenderTarget and passing it in. We've already implemented set viewport, so let's take a look at bind texture. We're going to get the texture from our texture map, and then if it is a multi-sampled anti-aliasing render target and it needs resolve, then we'll resolve the sub-resource and then update the needs resolve variable back to false. After that, we are going to bind it to our pixel shader, this by calling PS set shader resources. Otherwise, if it's not a multi-sampled anti-aliasing render target, we are just going to bind it with PS set shader resources. Note that when we are binding it for a multi-sampled anti-aliasing render target, we are binding the resolve shader resource view instead of the texture shader resource view. Let's take a look at updating the constant buffer. So what we're going to do is get the viewport's width and height, and we are going to create a model view projection matrix based off of the width and the height in the transform passed in the state. For the constant buffer data state variable, the first float is always 0, and then we have the screen width and the screen height. The last float is for the scale, and I actually do not want to scale this here, so I'm just going to pass in 1. For the transform, we are going to get the model view projection matrix data that we created right above. For the scalar data, we're just going to get the scalar data from the state object. For the vector and clip values, it's the same situation. We're just pulling them all from the state object, as well as for the clip size. Once all of these changes are made, we will call apply changes on our constant buffer, and then that finishes that function. Next, let's look at the bind geometry function. We're going to get the geometry entry. We will determine the stride based off of the geometry's format. There are 2 different structs in Ultralight for the 2 different vertex formats, so we will just use the size of those for the stride. The offset will always be 0. We will call setVertexBuffer and pass in the address of our VertexBuffer with the stride and offset, setIndexBuffer with the index buffer from the geometry entry, and then setPrimitive topology. We're always going to use triangle list. Depending on the geometry's format, we'll determine which input layout we are going to use, on whether we use the fill VertexShader's input layout or the fill path VertexShader's input layout. We only have two more functions to do here. So for apply projection, what we are going to do is we're going to create a transform matrix. We're going to set it equal to whatever the transform is that is passed in here. Next, we are going to create an orthographic projection matrix based off of the screen width and height. Lastly, we are going to transform this by our transform matrix and then return it. The last function here that we need to implement is our getAddressOfShaderResourceView function. So what we can do is we can get the texture ID from an Ultralight view by getting the render target associated with that view by calling render target, and then we can get the texture ID from that. Once we have the texture ID, we can look at our texture map and get that texture ID. And once we have that, we can get the address of the texture shader resource view. Now that our GPU driver implementation is complete, let's add this to the HtmlViewManager. Let's go into our initialize function and add this here. We've gone as far as we can with the HtmlViewManager right now. We need to actually work on our HtmlView class implementation before we can finish the HtmlViewManager implementation. Our HtmlView class will look like this. And there's going to be two adapters called the ViewListener and the LoadListener. We are not going to do those right this second. We're going to focus on the other things first. So we have our constructor, we have a function to load a URL, function to check if we're still loading, functions for firing mouse and keyboard events, a function for focusing the view, a function for setting the size of the view, setting the position, getting the world matrix for when we render it, a function for getting the address of the shader resource view, a function for getting the vertex buffer, the destructor, and a function for updating the world matrix. The default world matrix will just use the identity matrix, and then we're going to store an address to the vertex buffer for the quads that will be shared between the HTML views. We will hold a pointer to the GPU driver. We will have a ref pointer for the Ultralight view that is tied to this HTML view, and then we will just store the width, the height, the position, and then a boolean for whether it is transparent or not. Let's generate these definitions. First, let's take a look at the constructor. So we will need to assign our vertex buffer reference here. And we are going to assign the other variables, like our pointer to our GPU driver, our view, width, height, whether it is transparent. For the load listener and view listener, I'll comment that out and we'll come back to that. Once the view is created, we will want to update the world matrix so our height and width are up to date. Let's go ahead and look at the update world matrix, and it's going to be very simple. We will just create a scaling matrix with the width and height, and then we will transform that by the translation matrix with the X position and the Y position. In the destructor, we're just going to assign the view for the Ultralight view to be null pointer. For getting the vertex buffer, we're just going to return the address to our vertex buffer reference. When we want to get the address of the shader resource view, if you remember, we had just created that function in our GPU driver where we can pass in a view and get the address of that shader resource view. So we're going to return whatever that function returns. For getting the world matrix, we will just return our world matrix. When we set the position, we'll update the position's X and Y values, and then we will call update world matrix to make sure that is up to date. Same with the size. We will just update the width and height. We will call the resize function on our view, and then we will update our world matrix. For focus, we are calling the view's focus function. Now, this is useful because, for example, if I have this window focused, you see my cursor blinking. If I didn't have this window focused, then you would not see the cursor blinking. For a fire keyboard event, we're just going to call the fire key event on our Ultralight view. For firing a mouse event, what we're going to do is we're going to offset the mouse event X and Y position by our view's X and Y position. Since our view could be at the center of the screen, for example, and not necessarily be at the top left, we need to adjust the X and Y position so that whenever we click on a view, the mouse event that's being fired will have the coordinates that we are expecting. For checking if the HTML view is loading, we will just call the isLoading function from the Ultralight view. For loading a URL, we will call loadURL. Now that we have everything in our HTML view done, except for the load listener and view listener, which are actually optional, we can go ahead and finish the HtmlViewManager implementation. Inside of our update views function, which we will call this every frame, we're going to call update and render on our Ultralight renderer object. And then on our GPU driver, we will call draw command list, which will actually do all of the clearing of our render buffers and redrawing to them. When we create a view, once we successfully create the Ultralight view, we are going to create a new HtmlView object, or rather a shared pointer to it, and then we are going to call the constructor where we're passing in a pointer to the GPU driver, the ref pointer for our new Ultralight view, the VertexBuffer that is stored in the HtmlViewManager, the width and the height of this new view, and whether it is transparent or not. We will then just add it to our vector of views and then return that shared pointer. For firing a mouse event, we will just iterate through all of our HTML views and call fire mouse event. And for the mouse event, we will convert it to an Ultralight mouse event by calling that function. For firing a keyboard event, it's the same idea. We're just going to call fire keyboard event and convert it to an Ultralight keyboard event. One of the last things we need to do is we need to initialize the VertexBuffer for the quad that we're going to use between all these HTML views. So go ahead and put that right there. And now we can take this part out of our renderer class. So let's go back into the renderer header, and I can remove that VertexBuffer for the quad. And in the initialize function for the renderer, we can also remove the code here where we were initializing that. Now in our renderer, we need to actually create the function to render a view. So I'm going to uncomment that. We need to also include the file for our HTML view. Let's go ahead and generate this definition. I'm going to remove the code for rendering the quad. And for our render view, what we're going to do is, for our world matrix, we're going to get the world matrix from our view, and then we're going to apply the changes to that. We're going to update our input layout. We're going to set our PixelShader and VertexShader. We're going to set our ConstantBuffer for the ortho matrix and the world matrix. We're going to set our shader resource to be the address of the shader resource view for this view. So this texture that we're setting right here is going to be what we're sampling from in our PixelShader. We'll always use 0 for our offset. We're going to get the VertexBuffer for our view by calling getVertexBuffer, and then we are going to set our input assembler to use this VertexBuffer, and then we're just going to call draw. Now that our PixelShader is actually going to have a texture to sample from, let's go back into it and update it. So instead of just returning red, take that out, and now we will actually sample from our texture and then return that. Let's go back into our engine CPP file and take a look at how this would work. After we initialize our HtmlViewManager and we want to create a view, we will call createView and we will pass in the width and the height of our window so that the view takes up the whole window. If it's null pointer, that means it failed to create, so we will just call log critical error and return false. If it's successful, we are going to load in google.com and set the view as our focus. Down in our engine tick, when we are processing a mouse event, we will want to make sure that we fire it to our HtmlViewManager, and the same as when we process a keyboard event, we will want to make sure that we fire that to our HtmlViewManager. When we go to render, we actually don't need render quad anymore, so I'm going to take that out and go back here. So what we will do is when the frame begins, we will go through every single view that we have and we will render it by calling renderView and passing in that view. Before we call begin frame though on every frame, we are going to clear our device context states, and then we are going to call update views on our HtmlViewManager. We are clearing the states in case let's say we had like a geometry shader or something bound from the last frame. We don't want that to affect the rendering for the HTML views. So let's go ahead and run this and see what it looks like. Oh, and this failed. And the reason it failed is because in our Ultralight shaders, the entry point is actually called either PS or VS. So I need to go into the properties, change the entry point name, PS, and then for the Vertex shaders, it was VS. Alright, and you see that we get an error. What happened here was there's a file that we need to be able to access for HTTPS, and that file is the cacert.pem, and it is inside of our resources folder. We need to make sure that we set the resource path in our config options in order for this to work properly. So what we need to do is go into our HtmlViewManager, and where we are initializing our Ultralight values, we need to create a config object. We need to assign the resource path. So our resource path was inside of our executable directory. We had that resources folder that has the file we need to access. So we will just build this path like so. There's also another thing. This isn't why it crashed, but we need to assign the face winding. If we go into our config, by default, you will see that the winding is counterclockwise. However, we are expecting everything to be in clockwise order for our triangles. After we assign those, we have to tell Ultralight to use this config. So we will call setConfig. And let's run this now. Okay, so the program crashed and I wasn't exactly sure why. So I had to ask around for some help on the Ultralight Slack. And it turns out in the new version of Ultralight, there's another variable we need to set in the config. Since we're using a custom GPU renderer, we need to assign this use GPU renderer value to true. Now if we go ahead and run this again, you'll see we actually get in a web page. We can type something in and hit enter, and it's black whenever it's loading because that's how we coded it. Now, one thing you might notice is the colors look a bit strange, and that's because we need to account for gamma correction. So let's exit out of this, and we'll go into the PixelShader we had created. Now, for this, I'm just going to assume the gamma is 2.1, and there's these functions we can use for converting something to screen RGB space. All we will do is after we take our sample, we will call this toSRGB space function to correct it for the gamma. And now if we run this again, it should look closer to what we'd expect. Alright, that looks great. Now that we've successfully loaded in Google, let's take a look at how we would load in a local HTML file. Our file system is defaulting to our executables directory, so in that case we would start here. We're going to create a new folder, and we'll just call it web. And then let's open this up with VS Code. We will create a new file. We will call it example.html. This is our HTML file. And we will just have an input box. And that's all we will have on this HTML file. If we open up this website, we'll just have an input box and it will have some value inside of it. The way that we're going to load this is instead of using HTTPS, we will use file. We will have 3 slashes. And then we have to have the path to the file from our executables directory. So we'll go to the web folder, and then it was just inside of here. Let's go ahead and run this and see what it looks like. So just like we expected, we have our input box and it says some value. Next, let's take a look at implementing the load listener and the view listener for our HTML view. First, let's do the load listener. So we'll add a new directory and add a new header file for this. We're just going to inherit from the Ultralight load listener class, and we're going to be overriding this onDOM_ready function. So the purpose of this function is called once the document object model is ready. If we want to execute some JavaScript code on this view, we want to wait until the DOM is ready. So for example, I've gone ahead and opened back up the web page we had made in Google Chrome, so I can hit Ctrl-Shift-J and pull up the console for debugging. Now I want to update the value of this input box. And I know that for the ID, it's called myInput. I can get the input box's element like this from the document, and I can assign the value like this. So if I hit enter to run this code, you see it changed the value to test. So I'm just going to copy this code and go back into our program, and we want to run this on this view once the DOM's ready. To execute some JavaScript, we are going to call evaluateScript on this view, and then we are just going to pass in the JavaScript. And I'm going to use single quotes inside of our string instead of double quotes, so we don't have to deal with that. The next thing we have to do is inside of our HTML view, we just have to enable the load listener. So we will create a unique pointer to it. We need to add the include for this. And then in our constructor, we need to actually tell the view to use this. So we are calling makeUnique on our view load listener, and then we are setting the load listener for this view to be our view load listener. So if we run this now, you'll see that the input box is changed to test once the DOM is ready. Now this is important because if we just went into here, and say we copied this and commented out, and we go back into our HTML view, let's say that, just after we create the view, we decide, okay, we are now going to evaluate the script on it. Well, this won't work. So let's go ahead and run this real quick, and you'll see that the input box's value is not overwritten to be test because the view hasn't even been loaded in, but more so because the DOM is not ready. We need to make sure that the DOM's ready before we try to evaluate some script like this. Next, let's go ahead and implement the view listener. So we will create a new directory. We'll create a new header. We're going to be inheriting from the Ultralight view listener. We'll have functions for things like when the title changes, when the URL changes, the tooltip changes, when the cursor should be changing, and when a message is added to the console. This could be for errors, or it could just be if your JavaScript code is logging stuff out to the console. You'll also see that we have handles to cursors for the hand cursor, arrow cursor, and I-beam cursor. And this is just so that when we call onChangeCursor, we can actually override the current cursor that's displayed for this window. Let's go ahead and create the CPP file. What we are going to do here is just for the constructor, we're going to initialize the handles for our cursors. So we have the hand, arrow, and I-beam. When the title's changed, we're not doing anything. We could output a debug string with a new title to test it. When the URL's changed, self-explanatory, and the same with the tooltip being changed. One thing about the tooltip being changed is I've noticed on some websites it just gets spammed. So I'm not really sure what's up with that, if that's a bug or if that's intentional. When the cursor is changed, we're just going to have a switch case on the cursor enumerator that's passed in. And depending on if it's hand, pointer, or I-beam, we will update it. Of course, there are other cursor types, but I'm just not accounting for these currently. The last thing is onAdd console message, and for now I'm just outputting it to the output window when we have this happen. Now we have to go back to our HTML view and make sure that our view is going to use this view listener. So I'm going to uncomment out where we're declaring it, going to include the header file, go into the constructor, and here we can set our view to use this view listener that we've just created. And now if we go in to debug this, you'll notice that when we put our mouse over our input box, our cursor should change. Alright, and perfect. You see we get the I-beam cursor when we're mouse over input, and we have a normal cursor otherwise. Also, sorry if the rain is loud, it just started pouring down rain here. The next thing we're going to look at is calling a native C++ function from JavaScript. We're going to add a function for our HtmlView for this, just where we register the function. For now, we'll just call this register native C functions. In order to register the function, we first have to create it. So in this example, we're going to be creating a function to call the message box function. So I'm just going to call it native message box. Our function's return value and parameters are supposed to be laid out like so. All we are concerned with is the context, the argument count, and the arguments. The first thing is we're expecting this function to only have one argument, so that's the first check we'll do. If the argument count is not equal to 1, then we're going to output a debug string with the error, and then we're going to call JSValueMakeNull and pass in the context, and we're going to return this. And this is just pretty much saying that we're returning null. Otherwise, if we only have one argument, we need to make sure that it's a string, since we're expecting a string to pass into our message box function. So we are going to get the first argument's type by calling JSValueGetType, where we pass in the context and then the argument that we're checking, and we're just checking the very first argument. If the argument type is not a JavaScript type string, then we are going to output the error into our output window, and then once again we are just going to return null. The next thing is we want to extract the string from our argument, and the argument's type is JSValueRef. We can convert this to a JSStringRef by calling JSValueToStringCopy, and then we are passing in the context, the JS value that we're converting, which will just be the first argument, and then the exception if we want to store an exception. I don't care about that, so I'm just going to pass in null here. I need to get this JavaScript string ref into a C string in order to pass it into our message box function. The first thing I'll have to do for that is I need to get the length of this string, and I'm going to pass in the JS string ref that we just created. Next, I need to make a string buffer to store this string. So for that, I'm just going to use a unique pointer. And for the length, it's going to be the length that we just got. Next, in order to take our string and store it in this string buffer, we're going to call this function JavaScript string get UTF-8 C string. So the first argument is our JavaScript string ref. The next argument is the buffer where we want to store this, so we will just call the get function on our unique pointer. And then lastly is the buffer size, which will be the length. The last thing we need to do here is we just need to call our message box ASCII variant. And for the title, we will just have native message box, and then for the actual text in the message box, we will get whatever was passed in and stored in our string buffer. Once this is done, we are just going to return null. We want our JavaScript to be able to call this function, so the way that we will register it is like this. First, we are going to get the context by calling JSContext on our view. Once we have it, we are going to create a JavaScript string that holds our function's name. We need to create a garbage collected JavaScript function, so we will do that by calling JSObjectMakeFunction with callback, where we pass in the context, the name, and then our function callback. We need to get the global JavaScript object, so pretty much our window. We will do that by calling JSContextGetGlobalObject and passing in the context. Then we need to store our function in the page's global JavaScript object so that our JavaScript can access it. So we do that with JSObjectSetProperty, where we pass in the context, the global object, the name, the function, and then the last two arguments are optional. They are for the attributes or the exception, and I'm not concerned with either of those. Once we're done with the JavaScript string that we use for the message box, we are going to release it by calling JSStringRelease. Now that we have our function set up for registering our native C functions, what we are going to do is we're just going to call this, And now our HTML should be able to access these JavaScript functions. To test this, I'm just going to create a button, and the onClick for the button will be calling native message box, and we'll be passing in the button was clicked. So let's save this, and let's go back into our demo and run this. Alright, and now if we click on this, you see we get our native message box function was called, and the button was clicked, was passed in. Then we get a debug error. What? Oops. And the reason that blew up is because for the length, I should have been adding 1, and that will be for the null terminator. Let's go ahead and run this again. And we test it. Great. And nothing blows up. Perfect. So that is how we call a native C function from our JavaScript. And I guess that concludes this video. I was thinking of making a basic chat application using PNet and using this whole setup, so if you're interested in something like that, let me know in the comments. It should be much shorter than this video, I'd hope. But other than that, I hope this was helpful, and thanks for watching.